Welcome back to Methods of Operations research course. We are continuing our discussion on the integer programming algorithms. Until now, we learned integer programming algorithms for general integers, where the integer variables are greater than or equal to 0 and are restricted to be integers. And for these ones, in our branch and bound algorithm, simply we decide on to branch on a variable if it is not integer in the LP relaxation solution, and we branch on that variable by setting or including additional constraints saying that this decision variable is less than or equal to an integer value and a greater than or equal to an integer value. But as we solved the previous examples for binary variables, when the decision variables are binary, they can take only two values, either 0 or 1. And in the LP relaxation, when we solve the LP relaxation, either they will be 0 or 1 or a value between 0 and 1. And in this case, we branch on these variables by fixing their values. We set x equal to 0 or x equal to 1. Okay, so we fix their values. So it means that during the branch and bound tree, either a decision variable is free, which means that it is not fixed, and in order to show that a decision variable is free, we represent it with this symbol. Okay, I will use this symbol to represent that a decision variable value is not fixed, it is free, or its value can be fixed to 0, or its value can be fixed to 1. Okay, so in a branch and bound node, if we decide to branch on a decision variable, say for example x3, so the value of x3 will be fixed to 0 and to 1 in if we decide to branch on this x3. Okay, and for example in this part, again, if we decide to branch on this node, let's say this time on x1, so we fixed its value to 0 or to 1. So it means that in this node, in this example, in this LP relaxation that we are solving here, if we have, for example, three decision variables, x1, x2, x3 in this example, so, and if this is, say, root node, root 0, so it means that here x1 value is free, it is not fixed yet. X2 value is also free, it is not fixed, but the value of x3 is fixed to 0. Okay, so this will represent that, okay, x1, x2, x3, x1 is not fixed, x2 is not fixed, but x3 is 0. And it means that in all the nodes, all the branches down this one, the value of x3 will always be fixed to 0. But in all the branches that comes down this one, the value of x3 will be fixed to 1. And here, if we consider, for example, this branch, now x1 value is fixed to 0, so it is 0. The value of x2 is free, it is not fixed yet, but the value of x3 is fixed to 0. So starting from here, if you go up to root node, you can find all the fixations. Okay, here x1 value is fixed, so it is 0. Then here x3 value is fixed, so it is 0. But x2 is not fixed yet, it is still free. And free means this: the value of x2 is in between these two values. Okay, so it is free and it can take any value between 0 and 1. But if the value of x1 or x2 is fixed, then its value is either fixed to 0 or to 1. Okay, so this is just a representation. Okay, now we are going to solve this example, and it's important because in order to demonstrate, in order to apply this algorithm on paper in a class environment, we will be using such tables. So it is important to understand what is such a table. This table, it says that shows all the candidate problem LP relaxation optima for all possible combinations of fixed and free variable values in a maximizing, so it's important. It means that this problem is a maximizing mixed integer linear program. The x1, x2, and x3 in this integer program, MIP, is binary. They are either 0 or 1. But x4 is a continuous variable. So we have a problem which is maximization of something. We don't know what is it. We have some constraints. We don't know these constraints. But we only know that this x1, x2, and x3 are binary decision variables. And x4 is a continuous decision variable. We have such a mixed integer programming formulation. Okay? And we want to solve this using branch and bound algorithm. And for this, we are provided with such a table. So what does this table shows us? It shows us all possible fixations of these decision variables, integer restricted decision variables, and their corresponding solutions. Of course, before solving such a model, in real life, no one has such a table, okay? This is not from real life. This is just for demonstration purposes, because if you have this table, it means that you already solved the problem. You already know the solution of the problem. Our objective, our aim is to solve this problem and find the optimal solution. And the optimal solution is already in this table. What is it? So it's a maximization problem. So this column represents the objective function values. We need to find the maximum value where x1, x2, and x3 are integers. So have a look at this one. Can this be the optimal solution? No, because x1 is not integer. Can this be the optimal solution? No, x1 is not integer, x2 is not integer, x1 not integer, x1, 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 x1. Now look at this one. x1 is integer, x2 is integer, x3 is integer. So this last one is x4, and x4 is continuous decision variable, so it is not restricted to be integers. It means that this can be the optimal solution because all integer restrictions are satisfied, and its objective function value is 77. And if you continue, look at this one. Here also x1, x2, x3 are integers. The value of x4 is equal to 2. It can be, because it is not a binary 0-1 decision variable. It can take any value. And this is also feasible, and its objective function value is 28. So this is not integer. These ones already not feasible. And as you can see, there's another integer solution here. There's another integer solution. This is another integer. So we just look at the integer values. These are integer solutions, as you can see. Okay? So x1, x2, x3, we are just checking them, and they are integers. And among these alternatives that I marked, we need to find the solution which has the maximum objective function value. And as you can see, in this one and in this one, the objective function value is 77, and it's the maximum. And what is the values of x1, x2, x3, the decision variables? 0, 1, 1, 0.5, 0, 1, 1, 0.5. Actually, these are the two, these two are the same solutions. So if you have this table, you already know your optimal solution. Its z value is 77, the maximum objective function value, and x1, x2, x3 value is 0, 1, 1, and together with x4, it is 0.5. This is the solution. But the idea here is we are given this table to use in the branch and bound algorithm, okay, to demonstrate how this branch and bound algorithm will find this optimal solution. At the end, the branch and bound algorithm will find this optimal solution 77. But how it's going to find it? The idea is this, okay? And in this table, remember, in branch and bound, we start with the root node. Root node is the LP relaxation. And what is that? All decision variables will be relaxed to take values between 0 and 1. What does it mean? It means that all decision variables are free. So x1 is free, x2 is free, x3 is free. We don't need to consider x4 whether it's fixed or free, because we will never fix it because it is not integer variable. Okay, and now in the root node, I need to solve this problem. This is the LP relaxation of this problem, and I need to solve it. And the solution is provided here in this table. Okay, I will use this solution, and we'll say that, okay, if you solve this problem, you would get as the optimal solution, the value of x1 will be 0.2. because it's given here. The value of x2 is 1, the value of x3 is 0, and x4 is 0, and the objective function value. So you can represent the objective function value either with v or z. Okay, it is just a representation. In this table, it's represented with v, and its value is 82.8. Now, in the branch and bound algorithm, what we do, we need to make a decision either to fathom this node or to branch this node. And there are three reasons for fathoming. If you remember, we either fathom by infeasibility, fathom by optimality or integrality, and fathom by bound. And in this case, I will solve it in detail. None of these applies. It means that we need to branch. And branch on which variable? And as you can see, x2, x3 are already integers in this solution. The only non-integer variable is x1. So it means that we will branch on x1. Okay, so we can branch x1 equals to 1, x1 equals to 0. Now look, it's not important whether you write x1 equal to 0 and x1 equal to 1 to this side or vice versa. It's not important. Okay, you can write fixations to this left or right. It's not a problem. And now we have two open nodes. And what is the problem in this node? Look, we haven't fixed any one of the decision variables unless x1. x1's value is fixed to 1. The value of x2 is free. The value of x3 is free. So in this node, I am going to solve this problem 1, free, free. And how to find that solution? In this table, I'm going to find the 1, free, free, which is this one. And the solution is given here. Okay? So I'm going to use this solution 1, 0, 0, 0, and the objective function value is 74. And this, depending on this solution, I will make a decision whether to fathom or continue. Okay, so the idea of this table is this. So please understand it carefully. It gives us all possible solutions for all possible LP relaxations that I encounter during the branch and bound. I will not use all of them during the branch and bound tree. I will use only some of them, because when I fathom, some of the candidate solutions here will be fathomed and I will not need them anymore. Okay, so we will solve the example using this table. So we already learned that in a branch and bound algorithm, we need to make some decisions on selecting the nodes. For example, during the branch and bound tree, if let's say I have these open nodes, this one is open, this one is open, and this one is open. Which one should I select? We already learned two rules. The first one is the depth first search. The second one is the breadth first search. Okay, breadth first search. So in some questions, we may be asked to implement one of these rules. If we are asked to use depth first search, it means that we need to select a node which is in a lower level. Okay, so this is level 0, this is level 1, this is level 2, and etc. It goes in this way, and depth first search first selects a node in the deeper levels, but breadth first search selects a node which is in a higher level. And in this example, we are asked to use the depth first search. Also, we are given some other rules. What are they? Sometimes in some questions we are given such rules. It says that first evaluate the branch that fixes a variable value to 1. So remember, in each one of these branches, we are, let's say, branching one variable to 0 and 1. Here we are branching another one. So it says that if there are two open nodes like this, in one side we are fixing its value to 0, in the other one we are fixing its value to 1. Which one should I select first? According to this rule, in this example, we will first select this alternative where we fix its value equal to 1. Okay? So this is given as a rule to implement in this. In some examples, we don't have this rule. And if we don't have the rule, we can select one of them randomly, arbitrarily. But in this example, since we are given the rule, we need to implement it. And also, there's one more rule. It says that if more than one non-integer variables exist, so for example, we solve this problem and the value, let me say, let me give this example. Let's assume that we solve this problem, and when I solve it, the value of x1 is equal to 0.1, the value of x2 is equal to 0.4, the value of x3 is already fixed to 0. Okay, so this is the solution that I obtained from the table, let's assume. Okay, it says that if there are more than one non-integer variables, this one and this one, they are both non-integer. It says that branch on the one which is closest to integer. Okay, so the value of x1 is equal to 0.1, the value of x2 is equal to 0.4. Which one of these is closest to an integer? It doesn't say it is closest to 0 or 1. It says that closest to an integer. So we need to check both 0 and 1. So this value x1, it is closer to 0, not 1. And the value, I mean, it is closer to 0 by 0.1. Let me change this value to 0.7, and it may be more instructive. Okay, so let's assume that the value of x2 is 0.7. So x1 is closer to an integer by 0.1. x2 is closer to integer. It is closer to 1, not 0. And it is closer to 1 by 0.3. Okay, the distance of this value from 1 is 0.3. And it says that select the one which is closest to integer. Since x1 is more closer, the value 0.1 is less than 0.3, we will select x1 to branch on. So here, when branching, there are two alternatives, and we will select x1 because its value is more closer, its value is closer to integer. And it says that if still there are some ties, equalities, so let's assume that the value of x2 here was 0.9, okay? Then x2 is closer to 1, and its distance to 1 is 0.1. So x1 is 0.1, x2 is 0.1. So they are both equal. Which one should I select? It says that break ties by choosing the variable with smaller index. So if there are such equalities, still equalities, which one should I select? I will select x1 because its index 1 is smaller than 2, okay, according to this rule. As I told you, in a branch and bound algorithm, we may be given such rules, or maybe not. If such rules are given, we need to implement them. Otherwise, we can make the selections randomly, arbitrarily, and whatever alternative you use, you will obtain the same solution. I mean, these rules will not change the optimal solution. You will still find the optimal solution, but it will affect your path to this optimal solution. The branch and bound tree will be changed depending on implementation of these rules. And it's important, if you are given these rules, you have to follow these rules, okay? If you are not given, you are free to make your selections. Now, let's start this example from start to the end. Let's solve it and find the optimal solution. Okay, in the branch and bound algorithm, what we do, we start with the root node. Okay, I'm going to write root node here, node number 0. As I told you, in some books, they start with 1, but here I will start with 0. Okay, it is just a numbering. And 0, root node. Root node is always this one. All decision variables are free. They are continuous. Okay. So what does it mean? I need to look at this free, which is this one in the table. And it means that when you solve it, you will obtain 0.2100. This is the solution that we are going to obtain. And the value of Z that we find here is 82.8, this one. Okay, this is the starting point. While solving the problem, at the same time, I'm going to record my findings on this table on the right-hand side. Okay, it is very important to do this recording, and if you can do it correctly, it means that you understand the branch and bound algorithm perfectly. You understand what is a parent bound is, how do you fathom, how do you proceed in the branch and bound algorithm. Okay, so I will start recording from the root node, node number 0. Remember, this problem was a maximization problem. And in the branch and bound algorithm for a maximization problem, it says that initially, we don't know any integer solution, okay? We don't know any integer solution. So we call it the incumbent. Incumbent is the best integer solution that we find until this time. And it is currently 0. So for a maximization problem, the incumbent value will give us the lower bound, okay? The lower bound. The best integer solution that you find during the algorithm will provide you the lower bound for that problem. And currently, at the beginning of the algorithm, since we don't know any, its value is the worst possible. And for a maximization, the worst possible things is minus infinity, negative infinity. So I'm going to record this lower bound as minus infinity here. And what is the upper bound? Upper bound is the best possible that you can get at the end of this branch and bound algorithm. And we would get the upper bound from the parents, okay, from the parent bounds. And currently there is only one node that I solved. And when I solved this LP relaxation, I obtained 82.8. So what does this 82.8 means? It is the best possible objective function value that I will obtain after solving this problem. Okay, best possible. And for a maximization problem, best possible is the highest possible, largest possible value. It means that it is the upper bound. So I'm going to record the upper bound here. So this LB and UB represents the lower bounds and the upper bounds. And we are going to record the gap values between the lower and upper bounds. And how do we calculate the gap values? It will be calculated like this: best possible minus best integer or best found solution divided by best possible. Okay, so I will put this in absolute values. It cannot be negative. Okay, so best possible value. What is the best possible? 82.8. It is the upper bound for a maximization problem. And look, for a minimization and maximization, best possible and best found values will be different. For a best possible, for a maximization problem, best possible will be larger than best found. But for a minimization problem, best possible will be less than best found. Okay, they will switch. They will be switched. And what is best found now in node 0? This value is negative infinity. Okay, when we during the algorithm, if we haven't found an integer solution yet, so we don't calculate the gap. We just put a dash here. It means that there is still no integer solution. And in Cplex OPL, when you run an integer programming formulation, you will see exactly this one. When you look at the engine log, after running your model, if you open the engine log, you will see exactly this table. You will see the node, you will see the lower bound, which will be for a maximization problem, the incumbent value. You will see the upper bound and you will see the gap exactly in this way. Okay, now the second thing in the branch and bound algorithm after solving it node 0 is try to fathom it. Can I fathom, for any reason, can I fathom this branch? And the reasons for fathoming are either because of infeasibility, but the thing is, I already have a solution. I cannot fathom because of infeasibility. Fathom because of, let's say, optimality or integrality? No, because x1 value is non-integer. So I cannot fathom because of integrality. Can I fathom because of bound? And in order to fathom because of bound, this value over here that you find while solving this, it should be worse than the best solution that you find, best integer solution that we find. Currently, the best integer value is minus infinity. And the question, is this better, worse than the best integer solution for a maximization problem? No, this is better than this one. So I cannot fathom because of bound. It means that I need to branch. Okay, so branch. Branch on which variable? Branch on the non-integer value, and the only non-integer value is x1. So I'm going to branch on x1. So I'm going to write x1 equals to 1 to this side and x1 equals to 0 to the other side. As I told you, it's not important. You can write 0 here and 1 here. It's not important. And now I have two open nodes, and I have to select one of these nodes. And I need to implement the rules while performing this selection. The first rule says that I need to use depth first search. I need to select the node which is in a deeper level, and both of them are at the same level. So according to depth first search, I can select any one of them. Then it says that the rule tells me that select the branch which fixes the value of x1 to 1. And according to that one, next node should be this one. Okay, so the next selection will be this side. And what is the problem that I need to solve here? The value of x1 is fixed to 1, x2 is free, and x3 is free. And now I need to solve it. And let me look at this solution. 1 free free, which is this one. The solution is 1 0 0 0, and the objective value is 74. Okay, Z value is 74. Okay, so let me continue. So this, now we have solved this branch 1, and I will record its value here, node number 1. And what is the lower bound? Lower bound is the best integer solution that we found until now. And have a look at this solution. As you can see, all of them are integers, x1, x2, x3. All of them are integers. So it means that I can fathom this branch and fathom by integrality, or sometimes we call it fathom by solving. Integrality, okay? All variables are integers. And when you fathom a branch by integrality, I need to check my lower bound. I need to check my incumbent solution. So I'm going to represent the incumbent solution by z star. Okay, in the previous branch, my z star value was minus infinity because I haven't got any integer solution yet. But at this time, I have an integer solution with an objective value is 74. Now I need to compare the 74 with the previous one, which is negative infinity. Which one is better? For a maximization problem, 74 is better. So it means that I am updating my incumbent solution to 74. Now this is my new lower bound. Okay, so my new lower bound is 74. And what is the upper bound? What is the best possible? In order to obtain the best possible value, I need to look at the parents of the open branches. So the only open branch is this one. And the parent of this one is this. And the value of the parent is 82.8. It means that when you consider this branch, when you solve it, the best that you can get is 82.8. So the upper bound is obtained from the parents of the open nodes. And currently there is one open node and its parent gives us a bound of 82.8. So the upper bound is 82.8. Now the gap value will be calculated by 82.8 minus 74, best possible minus best found, divided by best possible, 82.8. This is the gap that we will obtain from node 1. So what gap is it? Currently, it says that your best possible value can be 82.8. This is your best possible value. And your lower bound is 74. And your optimal solution will be somewhere in between. It can be this one, it can be this one, it can be any point in between. So the maximum distance of your current solution from the best possible value is this much. So you are far away from the optimal solution in the worst case by this percentage. Gap is a percentage, okay? And we are far away from the best possible by this percentage in the worst case. The gap means this. Okay, let's continue with the branch and bound algorithm. There is one open node. It means that the next thing is to select that open node, this one. And here, the problem that we are considering is 0, free, free. And in the table, if you find 0, free, sorry, not that one, 0, free, free, we will find this solution. And here the solution is 0, 1, 0.67, and 0. And the Z value is equal to 80.67. Okay, now I need to make a decision. Can I fathom by infeasibility? No, I have a solution. We can fathom by infeasibility only look in these cases. If it says here infeasible, then we can fathom by infeasibility. If we have a solution, we cannot fathom by infeasibility. Can I fathom because of integrality? No, x3 value is non-integer. I cannot. Can I fathom because of bound? And the thing is, in order to fathom by bound, I need to check this value, 80.67. Is it worse than the best integer solution? The best integer solution is 74. and this value is 80.67. So it means that this is, in a maximization problem, it's important. This value is better than this one, so I cannot fathom because of bound. It means that I need to branch. And I need to branch on which variable? There is only one variable, which is not integer. So it is x3. And here I'm going to write this x3 value fixed to 1. And here x3 value is fixed to 0. And now there are two open branches. And I need to select one of them. According to depth first search, I can select any one of them. According to the second rule, which says that select the value which fixes, select the branch which fixes the value of x3 equal to 1. So I need to select this one next. So I number the node at this point, okay? We don't number the nodes as soon as we open them. The numbering is very important. When you look at the numbers on the nodes, you will understand that, okay, we first investigated this node, then this second one, then this third one. At the end, we will follow our sequence of solving these problems. Okay, in this node, which problem I am solving? It will be, look, x1 value. X1 value, is it fixed or 0? So if you go up to the root node, starting from here up to root, I see that x1 value is fixed to 0. So it is fixed. What about x2? Up to root node, I haven't fixed the value of x2. It is still free. What about x3? It is fixed to 1. Okay, so it is 0, free, 1, which is this one. And when you solve it, we obtain 0, 0.8, 1, and 0. And the z value is 79.4. Now I need to make a decision at this point. Can I fathom by infeasibility? No. Can I fathom by integrality? No. Can I fathom by bound? 79.4. Is it better than my incumbent, which is 74? No, in a maximization problem. So it means that I need to branch. And branch on which variable? There is only one variable which is not integer, which is x2. x2 equal to 1 and x2 equal to 0. Now look, I have 1, 2, 3 open nodes. So let me write the values here. For node 2, we forgot to record them. For node 2, what is the lower bound? What is the best integer value? It is still 74. What is the upper bound? The upper bound is the parent of the open nodes. When I solve this 2, what are the open nodes? The open nodes are these two. And the parent of these is this one. And its value is 80.67. Okay, so it means that the upper bound is 80.67. And the gap value will be 80.67 minus 74. Absolute value divided by 80.67. Now in node 3, what is the best integer solution? It is still 74. We haven't found any other integer solution yet. We still keep that one. What about the upper bound? Look, it's very important to understand this idea. The open nodes, after solving this tree, the open nodes are this and this. So the parents of these two is this one, and its value is 79.4. The parent of this one is this, and its value is 80.67. So the best one of these two parents will be my upper bound, the best. For a maximization problem, this one and this one, which one is the best? This one. So this will be my upper bound, okay? So 80 still it is 80.67, and the gap value will be exactly the same because the lower and upper bounds are the same, so they will be the same. Now I have 3 open nodes and I need to select one of them. According to depth first search, I cannot select this one. It should be one of these. And according to my rule, to select a variable which fixes value to 1, I need to select this one as the next node, which is 4. And now, which problem I am solving here? What is the value of x1? Is it fixed or not? If you follow the path up to the root node, you see that we fixed x1 value equal to 0, x2 value equal to 1, and x3 value equal to 1. And in the table, if you look this 0, 1, 1, which is this one, the value, the solution will be 0, 1, 1, 0.5, and the z value is equal to 77. Now I need to make a decision at this point. Can I fathom this branch? Because of infeasibility? No. Because of integrality? Yes. Because all decision variables are integer, so we fathom because of integrality. And when we fathom by integrality, I need to check. This is an integer solution now. Is this the best integer solution that we found until now? We need to compare this value with the previous one. The previous one was 74. You can see it here, the previous integer. New solution is 77. Which one is better? This one is better for a maximization problem. So now this is the new integer solution. So I put a star here. By the way, also in this table, as soon as you get a new integer solution, a better integer solution, it is better to put a star. We first get our integer solution 74 in node 1. So I put a star here. And in this node 4, I obtained a new better integer solution value. I updated my incumbent, so I'm putting a star here. And now my new incumbent solution is 77. Okay, what about the upper bound? For that, I need to check the parents of the open nodes. One open node is this one, and its parent is 79.4. There is another open node, and its parent is 80.67. I need to select best of these two, and the best is 80.67. It is still the same. And the gap value is updated now, because I am, instead of subtracting 74, I am subtracting 77. So a gap value will remain the same if the lower and upper bounds are the same. But if any one of them is updated, then the gap value will be changed. And look, we always start with a higher upper bound for a maximization problem, and we always reduce it. And our lower bound always starts with a lower value and increase. So the lower bound and upper bound come closer to each other. It means that the gap value initially starts with a higher value, and as we proceed, it either stays the same or it reduces. It never increases. The gap value never increases during a branch and bound tree. It either stays the same or reduces. Okay, it doesn't depend on whether this is a minimization or maximization. It always reduces or stays the same. Now, next thing in the branch and bound algorithm, I have two open branches. I need to select one of these, and according to depth first search, I have to select this one, the deepest node. So it is numbered as node 5. And which problem I am solving here? X1 is fixed to 0, X2 is fixed to 0, and X3 is fixed to 1. Okay, 0, 0, 1. And in the table, if you look at this 0, 0, 1, we see that it's infeasible. Okay, so this is infeasible. It means that we fathom by infeasibility. So node number 5, what is our lower bound? The best solution that we found until now, it's still the previous one, 77. What is our upper bound? It will be the parent of the open node. Open node is this one, and its parent is this, and its value is 80.67. And it means that the gap value is still the same. And there's only one open branch. I need to select that one. And here in this branch, what is the value of x1? It is fixed to 0. What about x2? It is free. What about x3? It's fixed to 0. Okay, 0, free, and 0. And if you look at this one, the solution is this, 0, 1, 0, 2. And the value of z here is 28. Now I need to make a decision, fathom or branch. And if you look at the values of these solutions, 0, 1, 0, all integers. So it means that we can fathom by integrality or by solving. But be careful, we can also fathom because of another reason. What is that reason? The objective function value here is 28, okay? And the incumbent solution is 77. This is an integer solution. And when I compare these two with each other, it's obvious that my previous integer solution is better than this value 28. So it means that I can also fathom by bound. So both of them are okay. You can write fathom by integrality or bound. And if you say fathom by integrality, then you need to also check if this value 28 is better than your previous incumbent solution. And no, my previous solution is better than this one. Okay, so let me record node number 6 here. The lower bound is still 77, the best integer solution. Now, what about the upper bound? Upper bound is found by the parent of the open nodes. And since there are no open nodes, it means that your upper bound is equal to your lower bound. It will be 77. And when all nodes are fathomed in the branch and bound tree, your gap will be 0. Every time in a branch and bound tree, when you finish the algorithm, your gap value will be 0. It means that you found the optimal solution. Okay, it is very important. The final gap is 0. And as I told you, if you check the engine log in the Cplex OPL, you will find exactly this one, and you will also see these stars. And stars means that the Cplex updated the best integer solution, 74, 77. When there is an update in the incumbent solution, it represents it with a star. And what is the optimal solution that we found at the end? The optimum solution is the last incumbent value that you found, okay, which is this one. So it means that we found the optimum solution in node number 4. And when you look at the node number 4, the optimum solution integer decision variable values and the objective function value is given. The objective function is this one. You can find it in your table, and the values of the decision variables, you can find it here. So this was a complete example that we solved using the branch and bound tree using such a table. So please do some practice by yourself on this and solve several examples to understand the idea better.